Good morning, and welcome to the Hammerspace webinar, Tier 0, a game-changing solution for AI workloads. I'd like to introduce our two speakers for today, our Hammerspace Chief Strategy and Business Development Officer, Tony Asaro, and our Senior Solutions Engineer, Jon Flynn. A few quick notes. You can ask questions in the chat box that you'll see on your screen, and we will answer those questions at the end of the webinar. There's also a 3-question survey that if you can fill out, we would love to see your responses to that. Thank you so much. And Jon and Tony, take it away.
Thank you, Trip. So let's jump right in. Just some context before we dig into Tier 0 of what Hammerspace is. So we are a software solution. We're software defined. We run on commodity servers and systems. We can use any multiple heterogeneous systems for the underlying storage. And we are, at the heart of us, a parallel file system. This parallel file systems is standards-based. This was critically important to us and our customers to use standards. So the standards that are within the Linux operating system using NFS 4.2 and PNFS. This was important to our customers for a number of reasons. Number one is they do not want to manage proprietary agents, clients, any modified clients. They want to be able to use standards throughout their system. We are a primary file system, and I put emphasis on that because we are not the physical storage. We are still the source of truth, right? We are the thing that is talking between the servers, the clients, and the data. So while we live on top of these other storage systems, we are the primary file system. And really, our design was for scalable workloads, to be able to create that level of parallelism so that you can easily scale and increase performance in a linear fashion. So it's not enough that we just use NFS 4.2. It's a standard that any vendor can leverage. What we've done is we've disaggregated the control plane from the data plane. And this allows us to independently scale our data plane so that you get that linear performance and you take advantage of that parallelism. I'm sure there's very technical people on this call, but I like using this analogy, and it's a simple one, but it is very accurate. The idea is that it's not necessarily about single vehicle performance, right, on a highway. It's about making sure that you have as many lanes as you need so that you never get into a traffic bottleneck. So it's really being able to create as many lanes as you need effortlessly, transparently, and simply when you need them so you never get into that bottleneck. And that's really what Hammerspace is designed here. We also have a global namespace. This is essential to our customers, and what we're finding within the AI spaces is that their data is distributed, but oftentimes their GPUs are centralized. So we are able to get the data from different locations by our global namespace. The global namespace, which is basically the presentation layer of a file system, can be made accessible and visible in multiple locations, regardless how physically far they are away. So whether your data is in San Francisco and you've got data centers in Germany, in Singapore, in Australia, in New York, all of that becomes a single logical system, whether that is on premises in your data center, whether it's in a colo or on the cloud. So we are native in the cloud as well. So it's not enough just to provide that accessibility and visibility. You also need to be smart about how you get data from point A, B, C, D, and so on, right? So this is where our data orchestration comes in. Hammerspace has unique capability at a file granular level to select which files you want to orchestrate to multiple locations or from multiple locations. Our orchestration capability is omnidirectional. There is no master-slave environment here. This is a peer-to-peer replication capability. And you could say, well, look, I have 1 million files in New York and I want to get it to my GPUs that may be in New Jersey or in Toronto or in some other location and say just these 1 million files or 10,000 files or 10 files. The number doesn't matter. It's the fact that you can select which files that you want to get. You can uniquely say, well, look, I want to send these 500,000 files to this GPU cluster. I want to send these 200,000 files to this GPU cluster. And it doesn't matter where those GPU clusters are physically stored, so that they could be on premises in your data center, or you want to put it into one of the cloud providers and use that as well. Oftentimes we have customers that either A, aren't going to invest in GPUs, and we're going to see over time that might be more and more of a condition as these GPU servers get bigger and bigger, and they become less affordable to lots of different companies that require the functionality but don't have the budget. They want to burst to compute. They want to burst to the cloud and take advantage of the cloud and their GPUs and being able to rent them on a short-term basis. So, or you have lots of GPUs, but you still don't have enough, right? And you're waiting 6 months for your next order to come in. You can augment what you have on the ground and use that in the cloud as well. So that's where data orchestration comes in. So what we have today and how Hammerspace is deployed in some very large environments and different customers is what we're used to, this sort of tier one model for our tier one for our AI workloads. So in this environment, this is actually built off of a customer that we have, Meta, but we have other customers that have several thousand GPUs as well. So this is a common architecture. So you see here that you have the GPU servers on top. On the left-hand side, note that our Anvil servers, this is our control plane, our metadata servers, are not in the data path. Hammerspace is communicating to the server clients via NFS 4.2, and this is the metadata path. Our Anvils are basically talking to the client, telling it where that data is stored in these storage nodes underneath. Now, these storage nodes could be anything, and I emphasize anything, that has Linux as its operating system and can mount NFS v3. So NFS v3, not NFS 4.2, as your storage node. You can use anything, whether it is a third-party NAS vendor, whether it's just a Linux server with NFS mounted to it, and mix and match everything in between. And you can scale these linearly and add, as you can see here, there's over 1,000 storage nodes in this environment, so it scales. And what we've seen here, because we are not in the data path, you notice the data path there, it's direct from the servers to the storage, right? There's no proprietary controller or network in between. It's a direct communication in that data path. And then this is how we get linear scalability, true linear scalability with no knee in the curve, with very little overhead for the IP network. So this is what we're seeing in our environments. And we are able to achieve this because we fully leverage the NFS 4.2 standard. We have disaggregated our control plane from our data plane, and we are able to use orchestration and data assimilation to move data around. Okay, so let's jump into tier 0. It's a very simple concept, but it has powerful implications. So what we're basically doing here is that we're using the storage that's inside of the GPU servers as a part of our parallel file system. And what we've done is we've taken a local asset, local storage, and made it into shared storage, basically make it a networked, accessible resource, right? So the idea here is to make this a part of your parallel file system that is accessible. Now, why we did this is because we have had customers that say, look, I'm buying these expensive GPU servers. I've got lots of storage that's inside of them. They are a wasted resource. And so they want to be able to use that resource so that they can use it as a part of their overall storage strategy. So let's expand on this. Oh, and yes, important point. It leverages the Linux operating system. We are not putting anything proprietary on these servers. This is something that we leverage that is built into the Linux operating system. And Jonathan will go into more detail as well. So fundamentally, you can create this scenario. You remember the tier 1 diagram, very similar here. You have now a pool of storage that is accessible to all clients that have permissions and access to it, as if it was a tier 1 or external storage. So now you can leverage all of this. And we'll talk about why this is important too from a lot of different reasons. For example, if you're using the cloud, when you rent out GPUs in the cloud, you're already paying for that storage, right? So you might as well use it as well. In many cases, you already have this, this is not being used inside of our customers' environments, and they want to take advantage of it. We had one customer that basically spent, an enormous amount of money on external storage. They were creating data so quickly that they ran out, and they had no more budget to buy any more capacity. Meanwhile, they had all of this stranded capacity inside of their servers, and so they asked Hammerspace to come in with tier 0 and leverage all of that. They literally put up 50 petabytes within a day running Hammerspace on, and it looks like they have hundreds of petabytes of need going forward just using tier 0. Now, this is not just restricted to tier 0. Remember, Hammerspace has eliminated data gravity. We have data orchestration. We are able to do tiering. We're able to move data transparently and live between systems. So in this environment, you can combine tier 0 with tier 1 in order to grow as you need to, flexibly take advantage of what you already have, buy more if you want it. The tier 0 may not be enough, so you want to augment that with external storage. You have those options to do it. Once this data is in there, once Hammerspace is running it, your data is not stuck in there. So it's not siloed data and it's not stranded. Okay, just wanted to do some analysis of the fact that SSD capacity is growing continuously, right? So today, what we're finding is that 30 terabyte drives are common, right? We're growing to 60 terabyte drives. They're available, and we'll see them become more mainstream over time. 122 terabyte drives in Q4 2025, and then become more mainstream in 2026. And we already know that 244 terabyte drives are in development. So the problem is that the more capacity is increasing inside of these servers, and so this wasted resource will become even more pronounced over time. Now, speculative, just in taking a look at where NVIDIA is growing in terms of what they're going to be doing in their environment. So today, you have about 60 terabytes of stranded capacity inside of your GPU servers. So there's typically 30 terabyte drives in there times 2. And as the 60 terabyte drives become more popular, it will become 120 terabytes. But in their next servers, their next generation servers, they are going to start putting in 4 drives instead of 2. So now with 122 terabyte drives, right, these things should actually coalesce at about the same time. You're going to have almost 500 terabytes of stranded capacity in a single server, right? And then, you know, as you start doing 244 terabyte drives, nearly a petabyte of stranded storage inside of these servers. So the time for tier 0 is actually pretty on cue for being able to take advantage of all of this. Okay, so why does tier 0 matter? So first of all, it reduces storage cost. And the investment in the infrastructure within GPUs and in AI is enormous. So anywhere that you can reduce cost, it's always a priority for our customers. The storage is already paid for. It's already a burden cost. It's already been paid for. You might as well use it. The analogy I like to use is like buying a house and not being able to use the garage, right? To put your vehicles in. Same sort of thing. You might as well use that storage. Also, power. GPU servers consume a lot of power. So in some cases, it's not even an issue of the cost of power. It's just being able to get access to power. We literally have customers that just have no more power in their data centers to give to their infrastructure in AI scenarios. We have customers that are looking for other power sources. You've read up on it, right? There are big companies that want to go out and buy nuclear power plants in order to power their AI infrastructure. So anywhere that you can ensure that power isn't being used and you can use it for other things, or the fact that you just have no more, by using the storage inside of the servers helps you to better control your power. Time to value is greatly accelerated because of this. Now, what do we mean by that? Well, when you have to implement this, the storage is already there. Implementing Hammerspace into this environment takes less than an hour. All right, so you can get up and running in this environment using it as a high-performance parallel file system in less than an hour. You didn't necessarily have to go out and evaluate third-party storage systems, which could take sometimes months in order for you to do. And then it simplifies the infrastructure management, right? So now you just don't have another system that you have to manage as well. And we're going to go into much more detail. That asterisk there was just a reminder to tell me this is an important thing to emphasize. So what we've been hearing from customers is that any way that they can reduce the idle time on their GPU servers, the CPU idle time caused by checkpointing, that's gold to them. These GPUs are quite expensive. They want to make sure that they're operating all of the time as often as they can to get the most out of their investment. And so any way that we can eliminate or reduce idle time. We'll never eliminate it. As much as we can reduce idle time for checkpointing, that is very important to them. So we have to, as people who've been looking at storage for years, it's not necessarily about IOPS and throughput. It's also about reducing idle time for checkpoint. As we discussed, the drive capacities are increasing, and NVIDIA is expanding the number of drives per server. Okay. We'll do questions at the end. I am now going to hand it over to Jonathan. Jonathan?
Thanks, Tony. So as Tony just mentioned, the increasing your theoretical or your actual utilization of your GPU clusters is an extremely big pain point for a lot of GPU farms. And so our initial look was to say, okay, checkpointing is one of the biggest things that affect good put or CPU or GPU utilization of these clusters. So let's put together a POC environment and show how Tier 0 can impact and accelerate these checkpoints. So the first item to look at is, what is a checkpoint? It is a crucial process that basically is periodically saving the state of a model during training. You can liken it to, I spent 2 hours working on a presentation and I saved every 10 minutes or I saved at the end. We've all had that moment where, oh crap, I've lost all my data. It's the same thing. In AI workloads, we need to save periodically so that if something happens, if something fails, we can easily come back from it. And so the idea there is the purpose is to prevent the loss of progress due to those failures and allow resumption from the last checkpoint so that we don't lose days, weeks, months worth of work. We only lose hours, minutes worth of work. Key benefits, of course, are reduce the risk of those catastrophic loss, those weeks, days, and months of work on this expensive cluster. A good example there is, Meta's Llama at one point with their 16,000 GPU cluster took upwards of 54 days. And so that's, almost 2 months of work. And if you don't checkpoint, you can lose all of it. The other parts of it is we enable scalability and flexibility for managing long-running jobs by having checkpoints, because we can increase the cluster size, decreasing the MTBF, and so basically increasing failure rate, but still be able to use large clusters to overall shrink our job time in order to get training done faster. And with this, with checkpointing, we have to monitor and balance our good put. We have good put, which is a percentage that allows us to understand our utilization and efficiency within the cluster. So with that in mind, it's important to understand good put a little bit more. It could be a new word for some of you. The idea of good put is that it is the amount of useful work completed in a given time period, say 24 hours. Good put factors out overheads such as checkpointing, system synchronization, and failures. So essentially, it is useful work or measure of effective productivity in the system during training. So it is while your training workload is going. How much time do I spend training versus how much time do I spend doing supporting tasks? A generally accepted good put target is 95%, and this depends solely on cluster size, storage configuration, storage speeds, network speeds. And so it's all a measure of how effective the overall cluster and cluster design is. So with that 95%, that actually leaves the remaining 5% for the non-productive time. This percentage is done using checkpointing, system synchronization, failures, all those supporting tasks of the actual training AI workload. Out of this 5%, only 50% of that, so 2.5% overall, is budgeted to checkpoints. So if we look at that in a 24-hour period, that's about 2,160 seconds. So in a day, I will have to do N number of checkpoints within 2,160 seconds. Now I say N because your checkpoint interval is dependent on your failure rate. So let's get into some of the challenges in checkpointing and continue through this because it's important to understand where those challenges are. I alluded to them a moment ago, but one of the first ones would be IO bottlenecks, right? So the idea of a checkpoint is we're going to be taking the memory state of a DGX system or a GPU system, and we're going to save some portion of that memory state down into a checkpoint file onto storage. So when we save it down, that's going to be looking at your disk write speeds, your network throughput. They can both significantly delay the checkpointing process, as well as file system and multiple other factors. But we have to look at those bottlenecks to understand what our write performance will be to make the checkpoint valid and backed up or have it reliably stored. Now, the next piece to it is that in a multi-GPU system like a DGX, data is often aggregated from multiple GPUs into files. And so the complexity arises as we step from single GPU systems to multi-GPU systems to, cluster-wide. So what does checkpointing do to our workloads? Well, every time training is paused to do a checkpoint, we create a dip in our good put, so our efficiency of our cluster. The more dips we create, the more frequent the interruptions, say hourly checkpoints for some cluster sizes, or say checkpoints every 10 to 15 minutes for very, very large scale clusters, we see a cumulative loss of time performing those checkpoints. And so the checkpoint speed becomes incredibly important, especially as your cluster size grows. Next big challenge is every time you do a checkpoint, you are saving the state of your model, right? And that model size will have a certain number of GPUs involved, will have a certain amount of memory involved. And every time you checkpoint, that memory state gets saved to disk or storage. And so the larger the model, the larger the cluster, the higher frequency your checkpoint, and the larger your capacity requirements become. And so retaining multiple checkpoints for fault tolerance or versioning adds some storage demands there, capacity-wise, that can be quite large. And lastly, obviously, with scaling the cluster size, in order to complete the training faster, we actually see that we become higher risk of experiencing a failure with mean time between failures. These DGX systems, these large GPU compute systems, are highly complex, and there's a lot going on. If you consider there's multiple PCI Express switches, Gen 5 PCI Express in today's systems, and those 8 GPUs, it becomes so complex that the MTBF can actually shrink quite fast as you scale your cluster size up. So a little bit more on MTBF. For this, I would like to make sure I give credit to Wes Vasky, who is a systems performance engineer at Micron. He built a model and presented this model of scaling your cluster, your good put percentages, and how often you need to checkpoint for your different cluster sizes. And it allows for understanding how much time you have for good put, how much time you have for each checkpoint, and what the impact of scaling your cluster might be. And so, a good data point here would be to start with a 2048 GPU cluster, which is about 256 nodes. In this size, you are looking at about a failure per day, simply because of how often things happen, right? How complex the DGX systems are, how complex the network is, et cetera. And so I can say that this data is fairly well curated from my understanding. And we did verify it with some of our own customer data as well. And the point here is that one failure per day for 256 DGX systems, 8 node GPU systems, will scale, right? As you go to the next size up, 4096 or 4096 GPUs, we see that you could experience up to 2 failures per day. And so how does this affect things? Well, how often you experience a failure helps to determine how often you should be checkpointing in order to recover from a failure, right? So if it takes me 12 hours to experience a failure, and it can happen anytime during that 12 hours, the question is, how much data do I feel is acceptable to lose, right? And so in this case, we want to checkpoint, maybe hourly, so that we can only lose an hour during that time period, right? And so the idea is, as you scale all the way out to say 16,000 GPUs or 2,048 GPU DGX nodes, you potentially experience a failure every 1/8 of a day. right? Which means your checkpoint interval becomes very, very small, and meaning you're checkpointing more. And so it becomes more and more important to ensure that your storage subsystem can handle those checkpoint writes as they come through. So what does this mean overall, right? Every time we do a checkpoint, we're affecting good put. And so we need to come up with a balance of our checkpointing interval with the number, with actual system utilization, because, we can checkpoint all day, every day, but then our good put is 0%, right? And we're not getting anything done. Again, as I mentioned earlier, the target good put percentage for most systems is 95%. That can't always be achieved. And simply, if I don't meet that target, basically I spend more time checkpointing and less time training my model, which means that my GPU systems are effectively not doing anything while we're checkpointing. So let's get into an example here. As I mentioned, Hammerspace looks at tier 0 and finds it to be incredibly valuable. We looked at multiple different workloads and found that in order to increase good put, the most efficient workload to target first would be this checkpointing process. So we put together a POC environment in our own performance lab in order to demonstrate this. And for demonstration purposes, I've narrowed it down to a single GPU node, simply because we don't have a 16,000 GPU server test environment, and trying to extrapolate that just doesn't really work, right? And so what we need to do is identify the performance it takes in order to get one node's memory written out, and then compare that with tier 0. So our test environment in this case happened to be 4 systems emulating a DGX B200, and then 2 of our DSX nodes acting as tier 1. Now, if you're familiar with the DGX B200, you'll know that it has 1.44 terabytes of memory associated with the GPU nodes, the GPUs in the system. And so worst case, your model fills the GPU entirely, and we have to take a snapshot of the entire memory. So looking at it from that perspective, I decided to test worst case scenario. I have to dump all of that 1.44 terabytes to storage. Again, our target good put is 95%. So I created a workload that uses FIO to simply stream that much data into n number of files to create the checkpoint data. An interesting point, or an important point to know, is this emulation just assumes a raw dump of GPU memory with no post-processing or serialization. So in most GPU environments or AI workloads, you may dump the memory of the GPUs into system memory and then perform some post-processing and serialization, and then dump from there into storage. The idea is that's going to take a certain amount of time no matter what. And I just wanted to show from memory to storage what it would take. And so we're only impacting that portion of the time. And so the thought here is, with my tier 1 being connected at 200 gigabit to my 4 GPU servers, my emulated GPU servers, we're looking at 200 gigabit as the primary bottleneck in this situation. We can see a checkpoint time taking about 167 seconds to tier 1. Now, one thing I will point out here is our performance lab is very modern. It was purchased last year. And so this is a highly performant tier 1 system, right? We can go up to 400 gigabit in our environment. I'm working with the switch vendor now to get that 400 gigabit stabilized better. Hence, I'm doing the testing at 200 gigabit. But the idea there is that Hammerspace's tier 1 environment with parallel NFS is highly performant. And so this is a very good number on a very good tier 1 system. So with that 167 seconds, we can start to do some data analysis. Using Wes's charts and a spreadsheet, we can identify that 167 seconds for a checkpoint would put us into a cluster size of approximately 640 GPUs. So with that cluster size of about 640 GPUs, that would require approximately 12 checkpoints a day. So if we continue to extrapolate that, we take the 12 checkpoints a day times 2.78 minutes, or 167 seconds. That would be about 33.36 minutes per day used in checkpointing. If we continue to extrapolate that, that puts us at about 202 hours, 203 really, and then about 8.5 days in a year wasted on checkpointing. And I say wasted, it's not really wasted because you're going to have failures and you're going to do restores. But the idea is we've spent 8.5 days when if we have something faster, we wouldn't necessarily have to. So that brings us to tier 0. So again, nothing has really changed. We have simply used Hammerspace data orchestration or objectives to simply say, if a checkpoint is written to this folder, it's going to go on that storage. If it's written in that folder, it's going to go on that storage. And so for the emulation, I had a folder that said, if I write to this folder, my objective says you have to write it to the local NVMe. If I write to that folder, it writes to tier 1. And so with this objective in place, very simple objective, which is great about the data orchestration portion of Hammerspace, we were able to get the performance down to approximately 45 seconds. It was really 44 and a fraction, but 45 seconds is the good number. I left the 200 gigabit networking in there, but I crossed it out because remember, with my objective, I'm now writing local to that tier 0 NVMe, the NVMe that's in the test system versus the NVMe that's in tier 1. So with that reduction, we can then scale it up like we scaled the other. Now, again, using Wes's spreadsheet, we can see that 45 seconds can allow for a cluster size of up to 2,560 GPUs. One thing to note here is, remember, we're talking worst case scenario where my data set, my model size is filling every single GPU to max capacity. And so if your model is smaller, then you might not be using all the memory of every GPU. And so your cluster size can grow well beyond this. But I wanted to show the data for worst case scenario where I have to dump the 1.44 terabytes of memory to disk every single time. And so with that in mind, we have 45 seconds. That gives us the cluster size of about 2,560 GPUs. If we keep the cluster size on parity with tier 1 to be able to do apples to apples comparison, that means that we'd be looking at 640 GPUs again and 12 checkpoints a day. So with that in mind, with 12 checkpoints a day at about 0.83 minutes, that gives us approximately 10 minutes per day, down from the 33 minutes that we saw in tier 1. If we continue to extrapolate that out, that takes us to 2.54 days per year versus the 8.5 days per year. Again, just to talk about it one last time, the way we did all this was using objectives, was using Hammerspace data orchestration. So an interesting or an important data point is to say that these checkpoints are not fully resilient until they've been written out from both tier 0 to tier 1, where we have multiple data copies, right? And so again, we use a Hammerspace objective that simply says, hey, once the checkpoint file is there and closed, you're going to let the AI workload resume and then copy it out to tier 1 in the background, which allows us to get resiliency without interrupting or impacting the AI training workload. In the case of tier 1, you can use similar objectives to get multiple copies or to prime GPU servers or whatever. But the objectives is what makes this possible. And the idea of bringing all of the siloed storage into one large parallel file system helps us to do this. So if we compare both of them, up top we have a table that I put together for easy comparison, and the top row is tier 1 using the 200 gigabit connectivity. The bottom row is using tier 0. And so as we step through these comparison points, we can see that tier 0 is approximately 3.7 times faster on checkpointing, which leads us to which takes us to a 70% less time spent checkpointing in the year. And so with this, it comes down to giving us back time. It also allows us to scale our cluster to much larger and still maintain our good put. So remember, good put, that measurement of utilization of the cluster is the idea here. The balance of time spent wasted doing supporting tasks or time spent enhancing and improving the model, right? And so with the fact that we get the checkpoints done faster allows us to increase our cluster size, get the job done faster while maintaining our good put utilization numbers. It also allows us, if we maintain cluster size, so instead of going larger, we just do it faster, on the same cluster, that 640 GPU cluster, we actually get back 143 hours of training time in the year. That was that that was the delta between the 8.5 days and the 2.5 days. With that time, we actually get more epochs. So higher utilization, right? Gets us to more work done in the year across these expensive clusters. And so with that in mind, Tony, did you have anything to add there, or should we move on to questions?
There were a bunch of questions on the chat, so I figured I did answer them, but I'll answer them as well verbally. So how is this different from a hyper-converged infrastructure solution? It's very different in that we are not stranded, and we can tier and use other storage as well. So the idea is being able to create an environment where there is no data gravity, right? And there's no proprietary solution or things of that nature. So that's why we called it Tier 0, because it implies that it is a tier. It can move to other tiers. It can move to other storage, things of that nature as well.
You mind if I emphasize something there, Tony?
By all means.
The other interesting point there is that, remember, we're based on open standard. We're not installing any special software, any special, parallel file system software or parallel file system client. And so in a hyper-converged environment, typically that implies that I'm installing my storage stack separately on top of the same node as my compute. And so it's a minor difference, but incredibly important. We're essentially using what's already in the kernel, what's already on the system, to export the storage and then mount it back, right?
There is no Hammerspace intellectual property on the server. Our Anvils and our DSXs are still external to all of that. So that's an important aspect of it as well. The licensing costs for Tier 0 versus Tier 1, our software license is the same regardless, but as I put in the note, obviously this will reduce cost because you're using a resource that you're already invested in. Is Tier 0 mandatory to have GPUs in the servers on day one? No. You can implement Tier 0 at any time, and even if you wanted to only use Tier 0 temporarily, you can remove Tier 0 at any time as well. So it's very easy to deploy in existing environments. In fact, most of the environments that we're in already have a brownfield, not greenfield opportunities. Excuse me. The CPU and memory consumption, obviously this is going to vary. Your mileage is going to vary. What we've found in the customers that we're working with is very, very little overhead in this environment. But again, it's going to depend on the traffic and the environment, the network configuration, and things of that nature. And so, yes, we haven't seen much. We are quantifying this as we go within these environments. But right now, the overhead has not even been felt. Under 0%. 0.0009% was the last calculation that I got. Can the admin define failure domains for Tier 0? Absolutely, you can. So you can create failure domains across other various different clusters within the GPU environment. You can, mirror data to an external storage system as well, Tier 1. So yes, there's best practices around doing that type of thing. Another question is, while checkpointing example for Tier 0, it seems that you would only be able to ignore the networking and the overhead of that if you have a single copy on a single SSD with a single server. Yes, that is the case. In our customer environments, we are doing mirroring across them in order to get resiliency. And again, because we're using capacity that was otherwise stranded, that seems to be a very good choice for customers, so that we're able to make sure that it's not all just within a single server. But in those instances where you do have to go over the network, we are a high performance, scalable parallel file system. So it's no different from that perspective. You're still going to get high performance. But where the checkpointing goes and where the trying to reduce idle time, the best practices allows us to optimize and utilize the local storage in order to reduce that idle time. I don't know if you want to expand on that at all, John.
Yeah, I'd love to. The idea is, you're exactly right. In order to maintain the efficiency and speed of the checkpoint, we want to write to local drives first. And we don't want to delay for the sync to Tier 1 or to another Tier 0 node in order to get our second or third copy of the checkpoint. So the idea is your latest checkpoint is vulnerable for a certain amount of time, right? And that time is really for our background process that scans to see if objectives have been completed, hasn't run yet, right? The idea is that would scan through, see that there is a checkpoint file that is closed. Once it's recognized that the file has been closed, it will then initiate a copy from the tier 0 system to either a tier 1, a tier 2, or another tier 0 system to ensure that you have data resiliency or a second copy of that checkpoint. The idea is we are balancing our good put, right? We want to get the AI workload running, back running as fast as possible. So we allow for a moment of vulnerability, but the idea is the last checkpoint is always there. So if something happens in the amount of time that it takes for the checkpoint to close and for the objective to kick in and make the data resilient, you still have one checkpoint before that to fall back on. So it's not like you lose everything in that vulnerability. And what we found is that this is acceptable to most because it allows for very high performant checkpoint, increased good put utilization numbers, while also allowing for the checkpointing system to work as intended, right? So again, the latest checkpoint is only vulnerable shortly after it's closed. Once it's closed, our objectives will kick in and begin migrating or destaging. Destaging is not quite right. The word not quite the right word because it doesn't remove the checkpoint from the local system. It simply makes it resilient across other tier 0 nodes or other tier 1 nodes.
This is where our data orchestration comes in.
Exactly.
So the other question is, do we see benefits of this working in traditional HPC environments not running AI? Absolutely. We focus on AI because obviously there's a lot of interest in it. There's a lot of focus on it. But this works in any environment. It can work with anything that's running Linux, right? So it could run in x86 machines, obviously GPUs. You can run this in ARM servers if you want as well. So we're not limited to where you can use the tier 0. So yes, to answer your question, we are very focused on other traditional HPC environments and use cases as well for tier 0 and everything that we do. Right, so we're not just focused on AI, but that is you'll see a lot of our messaging around that because that's where a lot of the attention in the market is right now.
Tony and John, thank you so much for this in-depth and informative look at Hammerspace Tier 0. For those of you still on the call, their contact information is on their bios on the page you're looking at. So please feel free to reach out if you have additional questions. And also stay tuned for a link to this webinar if you'd like to watch it again. And it will also include some of the highlights, distilled into bite-sized pieces. So makes it easier to digest. Thank you both again. And
thank you, everyone.
Look forward to speaking soon.